And what I'm going to do today should be helpful in doing, I think, what I would consider as one of the most important assignments from learning new things in this course. Of course, you will learn through the project to be able to work on a fairly recent research problem and gain confidence that will help you in your own thesis, I think. But in terms of the numerical methods, the set of tools that we are seeing now, it's probably one of the most powerful tools. They haven't yet found place in commercially developed codes, but there are some public domain codes that I will point out to you. COMSOL has some limited feature of these continuation methods. But I think not only on how to do it, but also you should be sensitized to what is possible when you're modeling. If you are modeling anything in your own thesis, what are the possible responses, how complicated natural systems can be. So throughout this course, we will pick up those kinds of examples that have very interesting behavior and that are inspired by chemical engineering, but there are also problems that are inspired by mechanical engineering as well, and solid mechanics, structural mechanics, etc. So I think we should get started. So what I'm going to do today is more like hands-on demonstration on a particular problem. So I will talk about what the problem is and then go about showing how I solved it in MATLAB. And then Mrinal will show it how you can set up the same thing in COMSOL. But maybe before I hand over to Mrinal, I will also talk about your assignment problem to give you an idea of what to expect so that you are prepared. Essentially what I want you to do is go through what I'm going through in today's lecture. I'm going through it on one problem and I want you to go through it on a different problem. But the mechanics of developing the algorithms should be a very helpful learning tool. Okay, the problem is, as you can see, I gave this problem in 1998 as an assignment to a graduate course. And several of these assignments were built on this problem, assignment 3, 4, 5, and 6, etc. We may not have the opportunity to go all the way through, but let's just understand what the problem is and what are the possible responses. This is based on a paper by Amundsen. How many of you know who Amundsen is? Very few. The next generation has come in of chemical engineers who don't know who Amundsen is. When we were growing up, Amundsen was the father of chemical engineering. He was a professor at University of Minnesota and the chairman of that department for a very long time and built one of the premier chemical engineering departments in the world. And then, of course, he retired and he moved to the University of Houston and continued to be active for another, I don't know, 10, 15 years, I guess. And in 1950s, he published this paper, okay, a paper on solution to these two equations. Where do these equations come from? They come from CSTR, okay? That is a continuously stirred tank reactor where you feed certain amount and say the flow rate is Q and you have a certain concentration and a certain temperature at which it comes in, and the product will leave at a certain temperature and a certain concentration. These are the two state variables. These are the two unknowns. So you might call this A naught, T naught as they are coming in. So the feed is coming in with a certain temperature and concentration at the flow rate. There is a chemical reaction that is taking place. It is a well-stirred tank so that the concentration at every point is the same. It's homogeneous. It's a lumped model. And what comes out, of course, you will have Q coming out, but what we are interested in is we can control Q. Q we would call as the distinguished parameter among a number of parameters that appear in this model. Okay? And that is something that we are going to control, change in a sense. It's a parameter in the problem. So if you look at the model, the first equation, what do you think the first equation is about? A, I said, is the concentration, right? V is the volume of the reactor. a parameter. I should tell you what V is. Okay, I'll give you the numbers for these. Okay, so V times A would be the amount of the particular reactant that is in the reactor. So d dt is the rate of change. So the rate of change of the composition in the reactor is equal to the difference between what comes in and what goes out, and how much of it is reactant. It's a mass balance. Okay, so the first equation is nothing but a mass balance. And the second equation then is an energy balance. Okay, and you can understand. So this is the input term. Okay, this is the output term, and this is the reaction term. The reaction term is the nonlinear term. What is the order of the reaction from your physical chemistry? We are treating it as a first order reaction. Why? Because it is a to the power 1. Okay, but where is the nonlinearity in that equation? In that particular equation, e to the power minus e over RT. Okay, T is the temperature in the reactor, and the rate of reaction, the rate constant, depends on the temperature according to the Arrhenius type of a reaction. But the product of A times that also makes it nonlinear, because there are two unknowns. A and T are the state variables, are the unknowns. There are two equations that we have written, one for A and one for T. Every other symbol that appears in here are all parameters, okay, that we should know. Now, if you take the second term, the rate of accumulation of energy equals energy coming in minus energy going out, the difference, T0 minus T. What do you think this one is? The heat of reaction. You guys are all doing Dr. Dooley's class now. Some of you are, right? You should know. Have you studied this equation in the particular course? Maybe not yet. I'm sure he will give you this. What do you think this one is? U is the heat transfer coefficient. So T minus T star is the energy that is transferred. So there is a jacketed vessel, and you have heat loss carried by the heat exchanger that is surrounding the vessel. Okay, that is the physical origin of this equation. From a mathematical point of view, Amundsen was more of a mathematician than a chemical engineer. He revolutionized. I would personally give credit to him. There are a number of chemical engineers, leading chemical engineers, who have revolutionized the education of chemical engineering. Bird, Stewart, and Lightfoot, of course, is one of the transport phenomena. But he basically introduced what I call the second level of synthesis in chemical engineering. The first level was unit operations as a common set of units that are applied in different chemical industries. The second one was the mathematical similarity in various processes, and that made possible things like Aspen simulators and stuff like that, because we could write one set of equations to a mathematician. This is an ordinary differential equation, whether it comes from a reactor or from a separator or from a chromatography, it doesn't matter. So he wrote a lot of books on mathematical methods. In fact, one of the first volumes of the 3-volume series is by Amundsen on mathematical methods of chemical engineering, matrix applications. So in that paper, they basically analyzed the solution of this particular equation. Okay? So we need to understand what do we mean by solution. There are two parts to it. One is a dynamical solution, which would mean if I make a step change to the flow rate or a concentration, how does A and T change with time? Does it reach a steady state, a new steady state? So that would be the time series solution that we would plot after solving this differential equation. It's an ordinary differential equation. We are going to see how to solve ordinary differential equation later on. Okay, and then we can answer questions about stability, etc. Now, what we are going to focus today is on the algebraic equations, which will mean the steady state. Okay, so I'm going to set this equal to 0 and set this equal to 0. So I'm going to call this as my first equation F1 and my second equation F2. But both F1 and F2 are functions of A and T. So I'm going to define a vector, a state vector X, which is going to consist of two variables A and T. And I have the two functions. Okay, so I can apply the Newton method to get a solution, provided you tell me what the parameters are. So all the parameters are given in this particular problem. Every other symbol that appears in this equation is identified for us. A specific number is given. Okay, but except for Q. Q is what I said as a distinguished parameter, meaning I'm going to change its values and see how the solution responds to it. Okay, so x is my state vector, and f is given by this vector. F is a vector consisting of f1 and f2, which I have identified here. Okay, those two equations. I'm going to set those two equations equal to 0, and I'm going to solve for the vector x, which consists of two states. So I'm going to apply the Newton method. So the first thing, what I'm trying to do is pose the problem and then show it how I solve it in MATLAB, okay, in sequence. So the first thing I'm going to do is impose the Newton method. Okay? So the Newton method is going to be x at n plus 1 is equal to x at n minus j inverse f. Okay, so I need to provide an initial guess for A and T. Okay, remember A naught and T naught are inlet temperature and concentration to the reactor. Okay. In the subscript T subscript 0, A subscript 0 are known values. The state vector, I need to make a guess, but that is a guess for the exit concentration T and A, or A and T. Okay, so what do I need to do to implement the Newton method? Once I post the numerical method, I'll go and show you how it is done, and then we'll come back and say, okay, now how do I implement Euler-Newton method on that, and then see what we get from that. Then we'll come back and develop the arc length method, and then go and see how to implement that in MATLAB. And if I am going fast, please stop me, because last lecture I polled individually a few people afterwards, even from PI, and the feeling is that it was pretty heavy material, okay, because a lot of it you're seeing for the first time. So by this lecture, I want you to be able to do it by yourself, because the next assignment for 2 weeks you'll be busy implementing these ideas on a different problem. Okay, so in the Newton method, then I need to program this particular line. Okay, that means I need to write a function that will accept some sort of an initial guess for A and T and return the two functions f1 and f2, defining all these parameters inside that function. The next thing I need for the Newton method also is a function that calculates the Jacobian. In this case, what would be the Jacobian J? What would be the size of it? 2 by 2. So what would J consist of? df1 dA, df1 dt, and df2 dA, and df2 dt. Now, I'm not going to spend all the time showing you how to do the analytical one, but I'll maybe show one, and I would expect you to kind of fill in the rest, but I will show you the function, the Jacobian function that I have written. So let's go back and maybe look at the very first one, df1 dA. How would I evaluate that? Okay. So I'm trying to now show you how I would calculate one of the four. You need to find out all the four of them. Okay. So what would df1 dA look like? All I need to do is go and look at the first equation. This is my first equation, and I'm taking the derivative with respect to A, right? It will be minus Q times dA with respect to dA, which is 1, right? Minus P V e to the minus R T e over RT times the derivative of A. Again, A appears linearly in there. So I've taken the simplest form for you to show the derivative. When you do it with T, what will you find? Of course, the first term will be 0. The second one will be minus PVA times e to the power minus e over RT multiplied by the derivative of minus e over RT, which is minus plus e over RT squared, right? So you need to calculate that analytically and be able to program that, okay? Any questions? Are there any questions from people in PI? Yes, Rashid, you are absolutely right. He was the father of chemical engineering in that sense. Do you guys know about George Davis? He was an industrial inspector in England. So those days, chemical engineering didn't exist as a field. Okay, so it was industrial chemistry. That is, chemists who learned how to build industries. And so there was sulfuric acid industry, nitric acid industry, ammonia industry, like that. So each plant will know how to take the raw material and produce that particular product. And there was no training of unit operations or anything like that. But this guy, Davis, was an industrial inspector. So he had the privilege of visiting all these plants to make sure that they all comply with safety standards and stuff like that. He was an inspector, right? And he was not only, he didn't just do the job and say, okay, 9 to 5, I've done my job. He saw similarity. You guys are using the same process equipment as ammonia plant is using or sulfuric acid is using. So he started putting together this idea of a common unit operations. The unit operations, the separation unit is the same separation unit, whether it is used in ammonia plant or any other plant. And that was how chemical engineering started as synthesis, the first level of synthesis of ideas from disparate groups into a core. And in US it was done something like, it was called Course 10, I believe, in MIT. And this that was, I think, probably done in University College London or Imperial College, I don't remember, one of them. So you're absolutely right. Thank you for pointing that out. But that was the first synthesis. What I'm talking about is the second level of synthesis, which is now we know all the unit operations. Several textbooks were written on unit operations, but the synthesis in terms of similarities on the mathematical modeling, the underlying mathematical models is the same no matter where the processes come from. And that was pushed forward by Burstewart and Lightfoot and Amundsen. And Amundsen tree, I don't know whether you have seen it, there is something called an Amundsen tree, which has on the various branches all the faculty members who are in different places in the US. And they are all, each one is a big shot, written a lot of textbooks, contributed to education. And Lapidus was one of Amundsen's students. I was Lapidus' student. I did my PhD with him. That's how I came to know about an interest in the educational aspect of it. Of course, Lapidus passed away halfway through my PhD, so I finished it with somebody else, Ron Andrews. But still, that's digressing away. So are there any questions from PIs on so far what we have talked about on the model? Nope? Okay. So what I'm going to do now is keep this picture in your mind. Okay, we have the equations and we will switch back and forth if needed. And I want to show how I would implement the very first method, that is a Newton method, to be able to get a solution for this particular problem for a given value of the set of parameters that you find here. Okay, plus a given value of q. I'm going to take q is equal to 1, very low flow rate. I'm going to see whether I can get a solution for that. Okay, so we will do that in MATLAB. And I'm going to call this as, I'm going to write, if you are not familiar with MATLAB, you may find this a bit daunting, but ask me to just slow down and explain. Okay. So I'm writing a script file, and in the script file I will take you through what I have done. And I will ask you to kind of identify from time to time what I'm trying to do. Okay. So in the first 4 lines, I have set up a sequence of calls that will give me the solution. On 4th line, x equal to Newton. Okay. That's going to give me the solution for that particular value of the problem. So what is happening? In line 1, it's fairly easy, self-explanatory, right? What am I doing? I'm creating a vector of length 2, the unknown vector x, and I'm giving an initial guess of 0.008 for A and 320 for T. Okay, that only I know. I can pack it in any way I want. So I've chosen to pack A first and T second into that vector. And lam, I don't know why I called it lambda, it's a distinguished parameter, that is Q for me. Okay, so I said 1, but I'm here putting it 0.1. So I want to find a solution starting with an initial guess of 0.008 and 320 at a parameter value of Q equal to 0.1. That is my first initial solution. And then I'm going to continue on that. So the line 4 is the crucial line. From there we have to branch off to see what all that particular line 4 is doing. Line 4 is making a call to a function called Newton, which I wrote. I will show you that. Okay. And then I have 2 functions, CSTR-F and CSTR-J. So what are those functions? CSTR-F will calculate the two functions f1 and f2, taking the initial guess x and taking the parameter value lambda. Okay, and this is a particular syntax in MATLAB that you should kind of get used to it. This is how you pass the name of the function. So the Newton method is a general method. You can use it to solve your own problem. In fact, if you understand this, to do your assignment should be fairly easy, because you will need to write maybe BRA2F and BRA2J. BRA2 problem, that's the one that you're going to solve. Okay, and x is the state vector. In your case, the state vector can be 21, 41, 81. It's a long vector. Okay, and lambda is one of the two distinguished parameters we'll talk about later on. So the first two are the pointers to which function will return you the function and the Jacobian. Okay, so this will return the Jacobian, 2 by 2 Jacobian, using that value of x that you see here and that value of lambda. Okay, I hope people at PI are able to spot where I'm pointing out on the board. The next one is the actual initial guess. That's the one that will take this value. Okay, and the next one is a tolerance. I want the function values to be, the two function values to be less than 10 to the minus 12, close enough to 0. And the last one is just a flag that I have put in to print out at every iteration so that I know whether it is converging or not. So in order to understand fully line 4, I need to open up three functions. One is the Newton method, the other one is CSTR-F, the other one is CSTR-J, because they are each doing something and returning the value. So I need to understand what they do. Okay. So let's open up the Newton method. This is the Newton method. Okay. So the first line, this is a function in MATLAB. It's a subroutine in other languages you might call. And on the left-hand side, I'm asking this function to return three numbers, R, I, and resid. I is the number of iterations that Newton took. Resid is the residual error, the last step, and R is the root itself. So R will be a vector of length 2 in this case. The first one will be a solution to A, the second one will be solution to T. And then this is the holder, placeholder for the name of the function. Okay, the FUN. dFUN is the placeholder for the name of the derivative function, the Jacobian. So when I called it CSTR-F and CSTR-J. So when the control is transferred to this, fun will be assigned that string CSTR-F, and dfun will be assigned the string CSTR-J, and then the call will be transferred to them. And of course, x here will receive the two initial guesses, tol here will receive the tolerance, and trace is the flag that will receive the value of 0 or 1. How I'm going to use each one of them is what you see inside. Okay? So I put a set of comments in line 2 to 8, and in line 11, I say if the number of input arguments is less than 5, okay, I can provide up to 5 input arguments. But if I choose not to provide, then that means I have not bothered to specify trace. Then it means I'm not interested in printing out every iteration. So I set trace equal to 0. So NARGN is a built-in function. MATLAB automatically knows how many input entries you have entered. Okay, and if that is less than 4, that means I have bothered not to specify both tolerance and trace. So I specify tolerance to EPS and trace to 0. Okay? EPS is a built-in function number in MATLAB. Okay, it is a machine precision, 10 to the minus 16 or so. So if I don't specify it, I say try to get the solution for the machine precision. And if the number of arguments is less than 3, I say, okay, I need something to get the job done, so please provide at least one guess, that is for x. If you're not provided the guess, I cannot do that. So I'll just, with an error, it means MATLAB is going to quit the function after printing out the error message. Okay? Any questions on that? So the Newton function is really not very difficult, and what you will find is that it can solve whether you have 100 equations or 100,000 equations in principle. Okay? And what does it do? The actual job starts in line 18. Okay? I'm setting for I equals 1 to 100, so I'm setting a maximum of 100 iterations. If it doesn't converge, it's going to quit. Okay? Otherwise, you will set up an infinite loop. Okay? So I'm saying try 100 times to see whether you can get a solution with that initial guess. Otherwise, quit. And this is the key. F equals FE val fun x. feval is a built-in function which transfers control to the, it's a function evaluation. Okay, feval stands for function evaluation. So it says evaluate that particular function fun. In this particular case, it is going to transfer the control to CSTR f. I'll show you what CSTR f looks like later on. And it's going to take the two initial guesses that were passed to it, and it will return the two functions, f1 and f2. That will be stored in that. Then I make a call to defun, which will have the pointer to CSTRj. And using the same initial guesses, it's going to evaluate the Jacobian at that point and get fd, the derivative of f. That's going to be a 2 by 2 matrix. Okay, and then if trace, that is the last value, is 1, then print out this one. What does it print out? It prints out the iteration number, the norm of x, the norm of f, so that I know whether it is converging and it is converging quadratically or not. Okay, and then this is the Newton method I wrote down. X equals, I wrote it down as xn plus 1 equals xn minus j inverse f, but in MATLAB syntax it is x equals x minus fd backslash f. Okay, and after I update the solution on the right hand side, I'm storing it in the same variable x. Why? I'm not calling it xn plus 1 different from xn, because I just need to use that automatically in the next iteration. If I put two arrays, then I need to take the old one and put it into the new. This does it automatically. So once this step is done, the old value of x, the initial guess that you gave is gone, but you have a new value of x, a better improved guess hopefully. Okay? And then if absolute value of f is less than tolerance, okay, then it says the job is done, and take x, that value of x that is converged, and put it into R. And that's what will send out the results, because R is one of the output. Everything on the output must be calculated inside this function. Okay, so if you go back, R must be set somewhere, I must be somewhere, receipt must be set somewhere, because these are the ones that are going to go out. Every other calculation inside is local. It will be forgotten. So once that's the purpose of a function. Take certain inputs, follows certain rules, calculates some output, and sends out the output. Okay, so in this case, it's going to send out only 3 outputs: R, which will be a vector of length 2, I, which will be a scalar number, the number of iterations, and resid, which will be a number which is the residual for that particular functions. Okay, so I'm setting R as equal to x, resid as the absolute value of f, and then I return. Okay, if it converges within 100 iterations, the exit will be through line 23. But if it doesn't converge in 100 iterations, the exit will be to line 25. So I'm still taking whatever the value of x at that time, the 100th iteration was, putting it into R, and calculate the absolute value of f and putting it into resid, sending that. Where did I set up I? I is the counter, it's always available. Okay, if it converges in 3 iterations, when it goes out, I will be 3. If it takes all the 100 iterations, when it goes out, I will be 100. Now I may want to use that to monitor how many iterations it took. That's why I'm putting that option. But you can write these in any way that you want. Basically, you need to implement this line 23. That's the key. Okay. Any questions? Any questions, guys, at the PI? Or anybody from outside of LSU? Because there are only 4 from PI and 2 from wherever you are. Okay. Any questions here? Is it there at the back? Are you able to see? Yeah. You don't have to write these functions. I will put them all, a copy of the entire thing that we do today on Moodle. Okay.
The notation for your Jacobian, I guess, or for the Newton method, for x equals x minus fd, then that slash.
Yeah.
Is that the negative? Is that the inverse of?
It is the inverse of fd. So the MATLAB syntax for inverting a matrix and multiplying it is this. Yeah. Okay. You could replace fd backslash with inv fd multiplied by. That
okay,
also.
So it uses the inverse function, the inverse built-in.
Yes, right. There are subtle differences in MATLAB. If you use the inv function, it will invert the matrix using one set of algorithms. If you use the backslash operator, it will invert it using a more efficient one. I think one uses Gaussian elimination, the other one I'm not even sure what it does.
So we have needed to like contemplate.
Pardon me?
Sorry.
Yeah, the question was, we had the discussion about line 22 for those guys online, okay? So what does this FD backslash F mean? That is, in MATLAB syntax, invert the matrix FD and multiply it by F, okay? But you can also replace it with INV FD multiplied by F. That is, we can replace these three characters with INV FD within parentheses multiplied by F. That will produce the same result. Okay? Yeah.
That will, what, can you explain more?
Which one?
That will F equals to span X, that, yeah.
This one?
Yeah.
Yeah, FEVal is a built-in function that transfers control to another function. So it evaluates the function. In this particular case, I want to evaluate the function that is pointed to by FUN. Okay, and maybe I will set up a breakpoint and show you what happens to this variable fun. Inside this function, all the variables are called local variables. So fun is a local variable which will contain the string, the name of the function that I'm going to solve, because I want to use this Newton method with any problem. So each one I may call it a different function name. So FUN is the one that will carry the actual function name at the time of execution. Okay, and FEVal simply makes a call to that particular function. It's a mechanism that MATLAB uses to transfer control to another function. So control is coming from one function and you want to transfer it to another function, but get back the evaluated value and store it in F. Okay, so if you see, if you're not familiar with debugging, I'll show you how to trace it. It really beautifully gives you a way of understanding how the flow of instruction takes place in MATLAB. Okay, so let me just quickly look at, okay, no questions there. Let's look at the two more functions and then I will run it, and with this stepping through to understand what actually happens. Okay, so the other two functions that I must understand are the CSTR-F and the CSTR-J. So this is CSTR-F. It's a function that I wrote. It's a very problem-specific function that you will write. Okay, and it takes certain input vector, so you will define what the length of the input vector will be depending on your problem. In my case, I have 2, and lambda is the parameter that I'm going to continue on. Okay, and here I have entered all the parameters that were given in the problem. In the problem statement, I had U, heat transfer coefficient, T naught, A naught, everything in the table, right? So I just entered all of them, and then my real computation starts in line 14, and there are very simple computations that are involved. So I know that X has 2 numbers, and the first one is a guess for concentration A, and the second one is a guess for concentration, the temperature T. Okay, so I take X1, put it into A. You might ask, why do I need to do that? You don't need to do that if you can find wherever there is T and replace it by X1, because you are internally using the map that A is X1 and T is X2. I want to copy the formula exactly as it is so that the chances of making a mistake is less. So I map the variable. I take X1 and put it into A, take X2, put it into T, take lam and put it into Q. Q is my parameter. Okay, and then the rest of the equations is very easy to understand. If you see this, it is exactly the same equation that was given in the problem statement. The first function and the second function. Now, why did I put 1, 1 and 2, 1? I'm making it as a column vector. Okay, so this function will accept a guess for X and a parameter value for Q and return the 2 function values. That is its job, and it will do that. Okay, any questions on that? So if you see each part, it's fairly easy to understand, but how all of them are put together and then we build on to continuation and other stuff is the real the challenge. So now the other thing I needed is CSTR-J. The structure is exactly the same, right? It takes X as a guess, okay, that you see here, and then lambda as the parameter. You initialize all the given constants and you do the same thing. Take X 1 and put it into A, take x2 and put it into T here, and take lambda, the parameter, and put it into Q. And what are these 4 lines? I showed only one of them. Okay, those are the various derivatives. If you compare the first derivative, I hope we have it, and I hope we have it right. Okay, minus Q, so this is J11 for you. Okay, minus Q minus PV times e to the power minus e over RT. Is that what we had? Minus Q minus P times V times exponential e over R over T. Okay, so you need to find all the other derivatives and make sure that I have not made any mistake here. Okay, so this will return J. Remember, anything that appears on the left hand side of this equal sign must be the one that is calculated and returned from this function. So the purpose of this function is to accept x and lamb and return J. J will be a 2 by 2 matrix. So all the elements have been put together now. Okay, so all we need to do is see how I can execute this in MATLAB. So let me go back to the script that I wrote. Where is that? Okay, so as I said, I'm explaining all this time what line 4 actually does. Okay, it makes a call to Newton. Newton makes a call, repeated calls, many times to CSTR F and CSTR J. Okay, and then it will come back with the result. And this is what is called cell in MATLAB. Whenever you put 2% sign and a space, it starts a new cell. So you can isolate different sections and execute only those sections. So I'm going to execute this section only. I'm just touching that. I hope it did that. Let's see. I guess I touched it several times, so you can see each time it executed. So how many iterations did it take place? Did it take 10 iterations? And remember, I said Newton method is quadratically convergent. Do you see a signature of that here? What does it mean? So what are these numbers? This is the iteration number. This is the function value. And this is the error in the function. Okay, this is the state. In this case, it's temperature, 307. Okay, and this is the function value. So what you see is, it's a poor guess. So the first time the function turns out to be 516, very large number. It's not 0. Okay, and then it comes down to 67. It struggles around that for a while. It goes back. It increases. But once it goes close enough, that is, the error is something like 10 to the minus 2. From that point on, if you have implemented the Newton method correctly, every time the error should become square of the previous error. If it is 10 to the minus 2, the next time it should be 10 to the minus 4. Okay? The next time it should be 10 to the minus 8. So it's following that pattern. That is your key signature that you have gotten your F and J correctly. Okay? If I put input a small error in either one of them, I will not see this kind of a convergence. Okay? It's just a sign error, for example, would destroy it. Now, why is it important to have the J as accurately as possible? Not for the Newton method. Okay? As long as the error is 10 to the minus 14, I don't care whether it took 10 iterations or 95 iterations. The final result will be correct. So even though the Jacobian may be in error, and you get the final result in 90 iterations, the final solution will be correct, but the Jacobian will be wrong. And you're going to calculate a lot of these things based on the Jacobian. What is one of the most important things you will calculate from the Jacobian? If I ask you the question, okay, you have the solution now, is it stable? Is it linearly stable? You have to calculate the eigenvalues of the Jacobian. If the Jacobian is wrong, your eigenvalues will be wrong. Your deduction about stability will be wrong. Okay? And the same thing happens when you're going to talk about the limit points. How do we calculate the limit points? So it is very important to notice that you do see a quadratic convergence. And that is the signature for the quadratic convergence. Okay? Any questions? Yeah?
For calculating the Jacobian, are there any built-in partial differential functions?
The question was, for calculating the Jacobian, are there any built-in functions available? The answer is yes. MATLAB has a symbolic toolbox which will take derivatives symbolically, and that's the only tool that you have. There is no other magical tool that's available. Some of the programs will allow you to calculate the Jacobian numerically. What does that mean? For that, you need to write only the function. Okay, so you will calculate the function at a certain value of x, and then you perturb it, x plus delta x. So recalculate the function, and then use something called the finite difference methods, which simply says what is the slope. How far does the function change when I perturb x1 alone? Then I can get both f1 and df1 dx, df2 dx1. And then I perturb the second variable and see how both the functions change. Okay. Now you can imagine if you have 100,000 equations, that's not an easy job. And you will find in your next assignment, you have 160 equations in one case I'm asking you to do. Okay. But you will see the pattern of derivative is the same. So there are basically 3 derivatives that you need to take. And the size of the matrix will increase, but the derivative expression is not that difficult to do.
And if you calculate them numerically, it's going to propagate the error.
Exactly. If you calculate it numerically, the errors in the Jacobian will slow down. You won't see quadratic convergence. It depends on how accurate your J is. And you will incur similar errors in the stability results as well as in the singular point results, because the singular points depend on the Jacobian being singular at a certain value of the parameter. Good questions. Any question from PI? Are you guys following the MATLAB part so far? Good. Thanasius, you need to translate Greek for us. Okay. I use Greek letters, but I don't understand the language. All right. Okay. So maybe let's just go through the stepping. So what I'm going to do is I'm going to set up a breakpoint. Newton here. Then I'm going to set a breakpoint here. I'm going to set a breakpoint here. Now, what I mean by breakpoint is on any of the executable lines, MATLAB indicates by a dash. If you go there and click on it, it will put a red dot. That means when execution comes to that point, it will stop execution and transfer control to you, so that you can look at the variables, and it's a very good way of debugging your own program. Okay? Once I have set up these breakpoints, I can go to the CSTR example and then start executing it. Okay? So when I hit execute, the control came to Newton. From Newton, it has come to here. So this is within the Newton function. I guess you have this one here, right? I can use this. Technology is really getting better. Okay, so here you see I started execution from the script, and I set up my initial guess, and transfer was controlled by Newton into this function. So what is the value for FUN? You can see it picked up the string corresponding to the function that I indicated when I called it. I called it, say Newton method, go and solve the CSTR F problem. Okay, so that is the pointer that is stored in there. So if you go take the cursor near the D function, it says what is the pointer there. If you take the cursor near X, it tells you what are the initial guesses that are coming into this function. Okay, and I guess I didn't, maybe I did specify 10 to the minus 12, I specified that as 1. So it has executed all these lines, and here it's indicating by green that it has stopped there. Okay, so at this stage, the pointer FUL will send the control to CSTR F, okay, with the value of X, and then it should get back so I can step one line at a time using this icon here. Okay, now the transfer was controlled from there to CSTR F, as I said that would happen. Okay, and inside CSTR F, I have X and I have lamb, which is Q for 0.1. So it's picking up all the values correctly as the transfer is going from one function to another function. This is a general concept of debugging. Most languages, Fortran, C, will have such a debugging feature, okay, allowing you to trace. So here I have defined A, and I have defined T, and I have defined Q. That line has been executed. But F1 will not show anything because it has not executed the particular line. It has stopped before executing that line. Okay. If I say step one more, it would have calculated f. So f will be now just one function value. The first function is not 0, it's minus 0.05. Not bad. Okay. And then go to the next one, and it calculated the two functions. So f will be now a vector of length 2. The second function is not very close to 0. Okay. Now this is where scaling becomes important. The reason the first function is close to 0 is not necessarily because we have a good guess, but because it has numbers that are very small to begin with. A is 0.005. Okay. And the temperatures are of the order of 300 or so. So we have two equations that are poorly scaled. So when you come for a continuation method, you need to rescale them so that both of them have equal weight in defining what is your measure of arc length. Okay. Now it is ready to get out of this function, so the arrow changes to out. Okay. What do you think would happen when I hit continue step? The call will return to the previous, wherever it was called from. Okay. And it will go and stop there. So it will take with it the function value f and assign it to whatever was on the left side. What happened here? Of course, you can always go back and see. Yeah, here the control went from through FEVAL to the fun, and I'm not sure what happened here. Why it stopped? Okay, let me try. Yeah, so it has executed that function. It came back. And I guess now I understand. I learned something new about MATLAB. What is the difference between green arrow and the white arrow that we saw before? Green is before execution and white is after execution, but before it goes to the next line. I think that's what it is. That's one of the things. You need to guess and see whether your guess is right in learning about MATLAB. Okay? So now f is defined in this function. Okay? So you continue with this. Transfer goes to CSTR j. Okay, and the same thing, the 4 values of j are calculated, it comes out, and there it is. Now FD is defined. It's a 2 by 2 matrix. Okay, and if trace, print that, and trace is 1. Okay, so it will print that. So if you execute that and then go to the MATLAB window, you will find that it has printed first iteration. These are the values that I printed. Okay, and now this is the key Jacobian update. Okay, so I'm going to just execute that. What do you think will happen now? It's going to go back, right? Because it didn't execute that. If you had taken that path, it would have returned. That means it would have converged, but it did not converge. And we know that by looking at the value of f. The norm of f, we want it to be less than 10 to the minus 12. Okay, it's not there. So it'll just go through this several times. Now you get the idea, right? I don't want to set up these breakpoints anymore. So take that out. And no, you can say continue with the rest. Once you're happy with it, just say continue with that. I guess I need to take this out. Continue. Of course, it gave you all the solutions. I didn't want you to see all these solutions because I executed the entire function, not only the first cell, right? It just went forward, okay? But it should have stopped at line 4, and what I would have had in the screen, the MATLAB window would be, this is all the way to arc length. I need to go back. These are all my debugging last night, calculating eigenvalue, etc. What we started this morning is just here, I think. Yeah, somewhere here, and then it goes on to execute all the other part. Any questions on that? That is the simple implementation of the Newton method. Okay. Now we want to go back and look at, yeah, question, please. Who wants to go first?
Okay. Yeah. Is it possible to pass more than one variable to those functions? So we're passing x, right? Is there a way to pass like t, something like that?
Well, it's not when you're. It is better to construct it as one vector with all the unknowns in there. Okay. You can pass many variables, but it becomes unruly if you want to pass each variable in the unknown as a list.
So just make it like we did with x, where it's a and t.
Right, right. I would separate the state variable from the parameter. So create a vector for the parameter, create a vector for the state. And the reason is, I have written this with Newton method, but there is a method called a function called fsolve in MATLAB. Fsolve has a very similar structure. So I can take the function that I have written, pass it to fsolve, and expect to get the solution as well from fsolve using the same structure. So that's the only reason. But you can write, when you're writing program, it's like writing an essay. You can write in any way you want. Your imagination is the limit. Okay, did you have a question? Yeah.
In your code, you're using a if statement to evaluate convergence. And then you're saying absolute value of, I think, f is less than tolerance.
Yeah.
And then you're actually printing the norm. Is there any difference?
Yeah, I actually, when I was talking about, I noticed that error, and I was hoping who was going to capture. The question for the people online is, when I am using in the Newton method, here I'm saying absolute of f less than tolerance, right? That's what you're questioning, right? What I should have is the norm of f, okay, if f is a vector. So why does it work? What does it mean? If I pass f to absolute value, I don't want a negative f to be treated as converged. That's why I'm taking absolute value, okay? But this is going to return two numbers, and only every one of those numbers is less than tolerance, it will satisfy. So that is the reason why it works. But a better way of doing that would be to replace this ABS with norm, because norm will then calculate the norm, which is the length of the vector f. Okay, that's probably the proper way to do that. Is that your question?
Yeah.
Yeah. It's a good observation. I just said, why did I do that as I was talking about it? But I was not addressing that. Okay, so what would happen here? I'm printing the norm because I don't want it to print all the x and all the f. Okay, but here I should have the norm also. I was doing this last night, late last night.
I just noticed something else also. I think when you went over x, like when you moused over x, it showed 3 values.
Yeah. The reason is, as I said, it ran through the arc length and everything. When you go to the arc length, I expanded x by the third variable, which is q. Right. So that is the current length of x in the space. What space is c? And the third value is q. You guys are very sharp in observing, and that is what you need. Learning the programming, if you are a sharp observer, you can learn what they are trying to do and ask the question, why is this, why is that? Don't read it like a novel, but read it critically, understanding every part of it. Okay, any questions from, okay. All right, so we know how to write the Newton method. The next step is the Euler-Newton continuation. What did we do in Euler-Newton continuation? Let's insert image. Okay, so conceptually what we saw in the last class was, given f of x lambda is equal to 0. Lambda is the distinguished parameter, x is the state variable. This could be of any length. Okay. In the Euler-Newton continuation, we want to generate a better guess. So in this particular problem, for example, if you're plotting A versus Q or T versus Q, you will get a curve like this. What we have done is only this, Q at point 1. So if I want to generate the solution for Q at 1 and 2 and 3 and 4, how do I do that? Of course, the simplest method would be to take the previously converged result and give that as a guess and apply Newton method. Okay? But we saw the Euler-Newton method as a better initial guess generator. Euler-Newton continuation is just an initial guess generator, but it's a better guess generator. What it does is it takes the tangent vector at some point and uses that project. Instead of saying the horizontal line gives you a better guess, the tangent line gives you a better guess. It's a linearization of this curve, and then say, okay, according to that I'm going to project what the next guess is, and then I'm going to apply the Newton method to go actually onto the curve for every value of Q. That is conceptually what Euler-Newton method does. Okay? And how do we implement that? We implement that by saying x at lambda plus delta lambda is equal to x at lambda. Now lambda and q are, I'm using interchangeably. Okay? Lambda is the distinguished parameter in generic sense. It is q for our purpose in this particular problem. It will be epsilon for you in your assignment problem. Okay? Plus dx d lambda multiplied by delta lambda. And this is evaluated at the current value of lambda. The derivative is evaluated at the current value of lambda. So I already know this. This is my current converged solution. And I need to calculate what this derivative is. And I need to pick this delta lambda. What is my length? How far am I going to go? That's the choice I need to make. Okay? So the focus then is on how do I calculate this dx d lambda. And we saw that in the last lecture by simply taking the derivative of this equation with respect to lambda. So if you do that, df d lambda is equal to df dx chain rule dx d lambda plus df d lambda equal to 0. Now it is on a vector equation, right? So f is a vector, x is a vector. So there are actually n components of that vector. Okay. So I already know what df dx is. What is that? That is my Jacobian. This is why I need to evaluate the Jacobian accurately. Okay. And what I'm interested in is calculating what this tangent vector dx d lambda is. That is what I need in here. Okay. So I can rearrange this equation as dx d lambda, which is a vector equation with respect to a scalar variable, as equal to, so I move everything else to the right hand side. Okay. So first I move df d lambda to the right hand side, it becomes minus df d lambda, and then I need to invert this, okay, because it is a matrix. So it's going to become minus j inverse df d lambda. So it is this the key equation in the Euler-Newton continuation. Once I get dx d lambda, I put it in here and I get a better guess, and then I apply Newton method on that guess. Okay. So any questions on that? Is it better than the last lecture? Are you guys able to get it? Any questions on those online? Is it better than the last lecture? Okay. All right. So now we are going to go into the MATLAB to see how I implement this. And when I do that, I'm going to do a forward sweep and a backward sweep. Okay. I'm going to go maybe from point 1 all the way to 30. Okay. And what you will find, the Euler-Newton continuation, when you reach a state like this, you're trying to project a solution there. There is no solution in the neighborhood, but it will still take that as an initial guess and jump to that. So you will get a curve that goes like that in the forward sweep. Forward sweep would be something like this, and the jump, and goes to the other one. And then I'm going to take the solution from the end, the converged solution from the end. I'm going to use the same Euler-Newton continuation, put it in reverse, backwards, and you will see how easy it is to do and how powerful it is. And what you will find is when it goes back, it comes all the way to here and then makes a jump to this. Okay, I'll plot this in two different colors so that you see both the forward path and the backward path. But that will tell us that there is something missing in between. That will be the clue. That will be the reason why you will say, okay, now I need to implement arc length continuation to turn around and get the intermediate part of the branch, because Euler-Newton cannot do it. Unless by magic I'm able to take an initial guess that is close enough to this and get a point. And it's not difficult to do. Suppose you construct this path, you can say, okay, I'm going to take this and take the average of these two and give that as an initial guess. You can try that. Okay? And then once you get a point on that, you can use Euler-Newton continuation forward and backward on that to construct both parts of the path. So if you want to learn only Euler-Newton, you say, I don't want to learn arc length, you may still be able to get the solutions by playing with tricks like these. Okay? So let's go to MATLAB and implement these ideas. So that is the second path, second part of the cell. From line 5 to line 13, I have implemented and plotted the solution. So the first thing that I do is define Q going from point 1 in steps of point 1 all the way to 30. I want to construct a whole series of solutions for different values of flow rate from point 1 in steps of point 1 to 30. Then I say SOLNF, that is a solution in the forward path, I just labeled it as F, is equal to Euler and XQ. Now Q is going to be a vector here. Okay? It's going to take all the values that were defined there. Okay? X is going to be what? The previously converged Newton solution for Q equal to 0.1. It should be actually a very good guess for the first iteration. Okay? So you need to generate the first iteration and then you can start the Euler-Newton. Why do you need to generate the first iteration? Why can't you use Euler-Newton right away? You don't have the solution to calculate the slope at the solution. To calculate dx dq must be calculated, the dx dq must be calculated at lambda. I mean dx d lambda must be calculated at lambda, right? So you must have a converged solution at which you want to calculate the slope. Okay, so and then I'm finding out what is how many entries are there. Now, how many of you are familiar with structures in MATLAB? Two. It's not a very difficult concept, but you should pay some attention to if you want to understand this code and use parts of this code in your assignment, you need to understand those. What I have done is I have put the solutions into a structure. SOLNF is actually a structure. The structure basically says it allows you to pack many types of variables into one symbol, SOLNF. Dot Q means it is going to contain all the Q values. Dot X would mean it's going to contain all the solution vectors. Okay. Dot norm, you can create anything else like that, and then you can address the whole thing as just one variable name, SOLNF, or a subset of it by saying SOLNF.Q. So here, this is a structure, SOLN.Q, and it just computes how many elements are there. This is for just plotting it. Okay. And then I create the figure 1, and I create two subplots. The subplot 1 is going to plot the Q vector, that is on the x-axis the parameter, against the norm of the solution for the first component, which is A, using blue color and circle as a symbol. And then I'm creating a second subplot that plots on the same Q axis the second component. So the first one is going to be for A, the second one is going to be for T. Let's just run this and see what it produces. I hope it produced something. I guess it didn't. I checked this last night and it worked. Set up. Whenever I get into difficulty, this is what I do. Set up a breakpoint and trace. Make sure that it works. So let's just start executing. So the first part would be executed. I have a solution. It's executed all up to this part. Here I'm stopping. Okay. I want to transfer the control to Euler. Oh, I didn't show you the function of Euler n at all. Okay. So these are the two solutions that was converged for Q equal to 0.1. And now Q itself is a vector containing 300 elements in steps of 0.1. Okay. So when I step through this, it should go to the function. Oh, it executed the whole thing. So it returned all the solutions in that SOLNF dot Q, which is the parameter, and then dot X. Dot X is a 2-column vector. The first column contains A, the second column contains the T. Okay, and then I'm going to just plot this for you there. Oops. Okay, so this is the blue is the forward path. Okay, so it came all the way up to here, jumped, and then continued on all the way to 30. Okay, and in the reverse path, I think it did all of them from the last time. So maybe let me just delete that and ask it to regenerate again. Let's see. Showing only the first one. Why is that? Oh, it's going to plot through the cycling. So it will add 1 point at a time. Oh, this is nice. I like this mouse. Okay. Every time it goes through that cycle, it just adds 1 more point. And it automatically scales the axis. And you'll find that around 7 or so, it should jump. Let me set a breakpoint there, and then continue. So that is your forward path. Okay, so it came all the way around 10, it jumped, and then went on all the way to 30, and it produces the A on the top part and T on the bottom part. That's Euler-Newton continuation. Okay, so every time it projected the tangent vector and constructed the solution. Now the reverse path is very simple. All I'm doing is now defining Q in the reverse direction from 30 in steps of minus 0.1 all the way to 1. Okay, starting from Q equal to 30. Because I already have the converged result that is stored in I guess I really didn't store it properly because I still give X as my initial guess that comes from there. Still it worked, okay, because that's only an initial guess. And from there, it's going to use the same method, Euler-Newton, but go in reverse direction and plot the solution for the next part. Maybe let's do that, and then we'll go and examine I guess it just plotted 1 point. You can see the plus green. Okay, that's for Q equal to 30. Now it's going to go through the loop several times. So I should have actually set it up here, then continue. Okay, so now you can see that it actually overshot when coming back and then jumped at a different position. So there is a hysteresis of solution for this case, and that's what made this paper an interesting one in the 50s, to understand the dynamic structures like that. Okay, so any questions? So that we know from this that there is a missing link that we need to find out. But let's just see how Euler-Newton is implemented. I think I'm going slower than what I thought. I thought I was going to hand it over to you today, but maybe not. Okay, let's look at. Again, it's a very simple program, right? It looks like it's a nice, powerful concept, but to implement it doesn't require hundreds of lines of coding, just a few lines of coding. So what does it do? Okay, on the very first line, it takes what the current guess is and what is the vector Q for which you want the Euler-Newton to be applied. Now, these need not be equally spaced. Okay, you can make it general enough that you can, and that's what I've done here. So in line 4, I'm counting how many entries of the Q are there for which I need to find the solution. So I need to set up a loop for n, okay, because there are as many parameters in Q. So my for loop goes from I equals 1 to n. For every value of Q in that, I'm going to try to solve the problem. But as I said, Q need not be equally spaced. So what I'm doing is I'm finding dq. dq is a vector which tells you the difference between two successive points. Okay, so it takes q, takes two successive points and calculates the difference and stores it. So what will be the length of dq? One less than whatever there was in q, right? Because when you're taking the differences between two numbers, that's what's going to happen. And then line 7 is straightforward. We already know. What does it do? It makes a call to Newton method, gets a solution. This is where I'm introducing the structure. Okay. Once the solution comes in x, x is just a local variable. It's going to be forgotten. Okay. So I'm saying what I'm going to return is a structure called SOLN, and I put SOLN dot QI. I is the parameter number. Okay. So I store actually what the value of QI is. Then SOLN dot X for the same parameter I the parameter that comes the index for the parameters. And there are two entries there. So 1 to 2 is X transpose. I just want to store it in a particular order. Okay. And so when I'm passing back, all I need to do is pass SOLN. The entire structure will be transferred back, including Q, including X. That's the beauty of this. You can, in your own mind, you can organize the thing in a better way. Okay, so now the Euler-Newton method continues. So I say if I is not equal to n, why is that? If I is equal to n, I don't want to calculate the last tangent vector. Okay, if I is not equal to n, calculate dx dq. Okay, but dx dq is the equation that I wrote down earlier, minus j times df dq. Now I already have this function written, CSTR j, so I don't have to worry about it. But I do need to write a new function called CSTR df dq. Okay, that's going to calculate the derivative of f with respect to q in those two equations. Okay, so I need to show you how to write that. Okay, so what I'm doing is I'm kind of breaking it up into parts so that all you need to do is find your own part and plug it in, and this framework will work for you on a different problem. Okay, but it will be your job to specify all problem-related information. Everything else, the logic has been figured out. Okay, and then what is this x? X is equal to x plus dx dq times dqi. Okay, so dx dq is what I've calculated. So I'm giving, this is my next best guess, and that is going to go where? It's going to go here, and it's going to go here. In this sense, it's going to go there. Okay, so I have updated my guess, a better guess for the Euler-Newton continuation. And of course, if I is equal to n, then break out and come out, and done with the job. So it is this one that constructs the entire solution for the whole range of parameters, right? And passes it as SOLN, which I can then plot, as I showed you in the previous one. So now, to understand the complete the understanding of this one, you need to take a look at DSTR df dq. But before I do that, I need to show you how I would calculate that. Okay, so let's go back to what would be df dq from the first equation? All you're doing is calculating the derivative of in all these expressions wherever q is. So df dq is going to be simply a naught minus a. Okay, and the same thing in here. Df dq is going to be rho cp t naught minus t, because q doesn't appear anywhere else. So it's a fairly simple derivative to calculate. Okay, and that's what you need to code in that function what I showed you as CSTR df dq. Okay, so I write a new function, I copy essentially the previous one, because all the things are essentially the same thing up to line 14. And then I have two statements, df dq1 for the first equation, which is a naught minus a, and df dq2. That completes the problem. So there is no mystery anymore. You know how to apply the Euler-Newton method, right? You need to have three functions that you need to write: the function, the Jacobian, and the derivative of the function with respect to the parameter. If you have that, then you should have the Euler-Newton continuation working. Okay, and we already saw how this thing works. So close that. Okay, any questions up to that point? Okay, so we know how to apply the Newton method, Euler-Newton method. All you need is a set of algebraic equations. When you're dealing with differential equations, you just convert them into a set of algebraic equations, and all the ideas apply once again. Okay, same ideas, and that's what Mrinal is going to show with COMSOL, and I will continue to lay out the arc-length method, and then maybe we won't have time to see the program today, and we'll continue with it on Wednesday. And so I will give you the assignment, assign it on Wednesday. Now, what is the idea behind, and then Mrinal, you can take, is it okay Wednesday for you to take over? Yeah. Arc length scheme. So what do we do in the arc length scheme? Okay. So we have these two equations, and we know that we need to reparameterize it, meaning I need to have an extended vector x, which is now going to consist of a, t, and q. I need to have an extended function, which is going to consist of f1, f2, which I already have, and then a new function I'm going to call as n. And I'm going to have to apply the Newton method on that, and you can apply the Euler-Newton continuation on that as well. Okay. So this is arc length. So I need to, this is a trivial part. I'm just expanding the vectors, q as an unknown. There's nothing much to do except you're going to resize your matrix, the vector x and the matrix, Jacobian matrix to 3 by 3. The key is to come up with a good specification for the extra constraint equation, because you have added an extra unknown, you have a degree of freedom which I'm going to use to define a third equation. And what I'm going to do is slightly different from what I did. In the last class I showed you a quadratic one, and there was a discussion at the end, if you remember, can I come up with something else? And I said plane. So I'm going to illustrate this with a plane. Okay? So it's going to be W1, it's a weighting factor, times dA ds at the current value, okay, multiplied by a minus a naught plus W2 dt ds at the current condition times t minus t naught plus dq ds times q minus q naught equals s minus s naught. This is the arc length equation, additional constraint I'm going to use. So it's essentially a tangent plane type of a constraint. So these are all known. Okay, do I know that? Not quite. I know it in terms of dA dq. So I need to reformulate it in terms of dA ds. Okay, and a naught t naught are the current reference solution. So you need to have a converged Newton method, and then you turn on the arc length method. So you'll need to collect a lot of these parameters. And what is W1, W2? These are, in this particular problem, particularly very important. In your problem, it won't be that important. Here it is important. Why? Because A is very small number, 0.005. T is a very large number of the order of 300. So if I'm having this equation with W1 equal to 1, W2 equal to 1, the definition for the arc length is going to be dominated by temperature, not A naught. Okay. So what I need to do is I need to boost this number up. So I'm going to put a weighting factor of 10 or something, and I'm going to scale this down. Okay. So I'm going to maybe put a scaling factor of 0.01. Okay. So, and this is something that I choose. Previously I was choosing delta Q. Now I'm choosing delta S arbitrarily. Okay. But I'm solving for A and T and Q. All these are unknowns. But the derivatives I'm going to be able to calculate. Okay. So this derivative, and this derivative. How do I do that? I do that by using the fact that I can write dA ds as dA dq times dq ds. Okay, I already know what dA dq is, the tangent vector. I have calculated it, right? So I do the same thing for this, dt dq dq ds. So I have dq ds as a common factor in everything. I can pull that out, and I can calculate how does q change with s, because I'm going to control s, and I want to see how q changes from that equation. So that will give me the starting point. Maybe that's a place I think we should stop, and when we come back, we will develop the Newton method for the extended system. So right now you should understand what the extended system is. I've extended it by adding a third variable and by adding a third equation. So it is these three variables from these three equations I need to solve using the Newton method. So I need to construct a function in MATLAB. I would call it as CSTR arcf. Okay, CSTR f arc. Okay, this is the function for the arc length method, and this will expect, it will send three values and it will expect to get three values, and there are those three functions. And the third function is what I just wrote down. Okay, you need to take the Jacobian of this 3 by 3 matrix. So you will write another function called CSTR J arc. Okay, again it's the same idea, but now you already have this 2 by 2. I'm just filling the rest to make it into 3 by 3 to extend it, and then you pass it to Newton method, and that works, and then you construct Euler-Newton on top of that. Okay, so we will see those parts, and then you should be able to solve any nonlinear problem with the continuation method. And Mrinal will show you how to do the same thing in COMSOL. COMSOL does not have the full arc length feature built in. It has a continuation feature built in. Okay, but it will fail when you have a critical point, and so he can show you how to implement the idea that we have developed, trick COMSOL into also solving arc length scheme for algebraic equations. He's trying to figure out how to do it for differential equations also. Okay, so we are all learning at different parts and that's the advantage of a nice graduate level course. I hope you found this lecture to be a bit easier than the previous one. If you have any questions, please feel free to drop by or send by email, whatever. Okay? All right, see you on Wednesday. I don't know why I'm going there. I can control everything.
Please try out these codes over today, tomorrow, so that Wednesday will be
Yeah,
there.
I will put up all these codes. Look at them. Yeah, I have uploaded the last lecture, and I will upload this lecture sometime today. I am going to a PhD exam, but in the afternoon, expected. Oh, you have already done it? Oh, you need to. All right. Yes, Mama, waiting for you. All right, okay.